Welcome to this video on polynomial roots and factors. In order to understand the concepts of this video, one first has to understand how to do polynomial long division and synthetic division. If this isn't something you've seen in a while, I recommend you go to my YouTube channel, Recede Low Math, and check out this video. In this video, we'll look at polynomials and we'll learn how to factor them. We'll also learn how to take polynomials and find out what particular x values will make them equal to 0. We call these numbers roots. More on that later. It turns out there are 4 numbers which, when plugged into this polynomial, will make it 0. And in this video, we'll learn some theorems about polynomials. We'll learn how to find roots, how to find factors, and we'll see the connection between roots and factors. Let's start with some vocabulary you're going to hear a lot during this video. A polynomial is a bunch of terms added together where each term consists of a number times a power of x. And you may look at this polynomial with 4 terms and say, well, not every term in it is a number times a power of x. But if you're willing to extend your concept algebraically of what a term is, you can see that any term, even when it doesn't appear to be expressible that way, can be written as a number times a power of x. And when you add up a bunch of terms like this, you get a polynomial. Coefficients of a polynomial refer to the numbers in front of the powers of x. You can see them here in red. 1, 6, negative 8, and 1 are the coefficients of this polynomial. The degree of a polynomial is the highest exponent. Factors of a polynomial are what we get when we take a polynomial and express it as one polynomial times another. I'm not going to show the work here, but the product of the 2 polynomials on the bottom, if we were to work it out, would equal the polynomial on the top. So you can see how the bottom one has 2 factors. The root of a polynomial is a number which, when plugged in for x, results in 0. Here's an example. For this polynomial, we could say that x equals 4 is a root. And the reason we would say that is because when you substitute 4 for x and you work it out, you do in fact ultimately get 0. 4, by the way, is not the only root of this polynomial. More on this kind of stuff later. Here's some additional vocabulary. When you hear me say integer, I'm referring essentially to a positive whole number or a, quote, negative whole number or 0. So integers can be anything like this. When you hear me say a rational number, I mean anything that's an integer or a fraction of integers. So, for example, 3/5 is a rational number, as are all integers. When you hear me say real number, I'm referring to all the rational numbers, or every possible fraction of integers, plus numbers like 2 plus radical 5 or 5 pi over 6, things that cannot be expressed as a ratio of integers. And when you hear me say complex number, I mean anything that's an integer, a rational, a real, or a sum of a real and a non-real term, such as 3 plus 2i. Now let's get into the bulk of the video. This video is produced with 2 major components. First, we're going to look at some idea development, some important theorems about polynomials and why they are the way they are. And in the second part of the video, we'll look at a practical application This would be the portion of the video where you would learn the procedures that you would use most likely in a math class. Let's start with the idea development portion of this video. We'll start with some polynomial theorems, the first of which is called the remainder theorem. I'll pause while you read this to yourself. If you're not accustomed to reading mathematical theorems, or even if you are, this may sound kind of abstract to you. So let's look at an actual example here. What this theorem is saying is, if I have any polynomial, such as this one, and any random number, such as, say, 4, that I could take this polynomial and essentially divide it by x minus 4 by expressing it as x minus 4 times some polynomial plus some number. In other words, what the theorem is saying is that I could fill in the two blank spaces in such a way that these two polynomials are equal to one another. And furthermore, because of the uniqueness expressed in the theorem, we know that there's only one way that this can be done. Now, how one goes about finding that way is a separate issue. We're not in the how-to portion of this video right now. But I have done the behind-the-scenes math, and it does turn out that these two polynomials are equal to each other. And if you need to convince yourself, hit pause and work out the one on the right, and you should get the one on the left. But if these polynomials are equal to each other, then they must be equal to each other when x is 4 in particular. And so let's compute p of 4 by plugging 4 into both polynomials. According to the theorem, p of 4 should be 10. And you can see obviously on the right side that if we were to work that out, we would clearly get 10. But it turns out if you worked out the one on the left, you'd get 10 as well. If you're a little confused about what is it that I'm doing here, I'm just explaining a theorem in one of the findings. This isn't something you would actually do. You will need to use this theorem to solve problems, but you wouldn't be solving them this way. I'm just trying to give you a sense of what this theorem is actually saying. Let's take that same polynomial again and divide it by x minus 3 and express it this way. It turns out this theorem has an interesting statement if this remainder value turns out to be 0. And what it tells us is that if these two polynomials are equal, then x minus 3 must be a factor of that polynomial. And you can see that if we plug 3 into the right side of the screen, we clearly would get 0 as a result. But it turns out that p of 3 actually does equal 0. And this concept gives rise to an interesting new theorem called the factor theorem, which is a special case of the remainder theorem when r is 0. The factor theorem states that x minus c is a factor of a polynomial if and only if p of c equals 0, or restated, if and only if c is a root of that polynomial. And to give you a sense of what the factor theorem says, take this polynomial as an example. Now it turns out that if I were to plug -2 into this polynomial and do all of the work, it turns out that the result would be 0. Restated, -2 is a root of this polynomial. But it turns out that if we were to factor this polynomial, x plus 2 would be a factor. In other words, x minus a -2 would be a factor of this polynomial. And this is just an example of what the factor theorem says. Stated more plainly, if negative 2 is a root of this polynomial, then x plus 2 is a factor. And conversely, if x plus 2 were known to be a factor of a polynomial, then it shouldn't be surprising that that polynomial evaluated at negative 2 works out to 0. One more theorem of importance is called the fundamental theorem of algebra. The fundamental theorem of algebra states that every polynomial has a root. It's a little more complicated than that, but we'll simplify it down to this one sentence. But the corollary to that is if every polynomial has a root, it turns out that every nth degree polynomial has n factors and therefore n roots. To show you an example of what the fundamental theorem of algebra would say in a specific case, look at this polynomial here. It turns out that 3 is a root to this polynomial. How would you know? Well, we're not in the how-to portion yet, but if you were to plug 3 into this polynomial, you would in fact get 0 as an answer. And according to the factor theorem, if positive 3 is a root to this polynomial, which it is, and you could check for yourself, then x minus 3 is a factor of this. And if you divide it by x minus 3, you will in fact get this factorization. But look at the cubic polynomial as the rightmost factor here. It turns out that that thing also has a root, which happens to also be 3, meaning that I could factor x minus 3 out again and get a second degree polynomial. Now, as far as the roots of this polynomial go, 3 is a root, 3 is a root again, and the polynomial on the right turns out to have 2 roots, 2 plus radical 5 and 2 minus radical 5. Remember, I'm not in the portion of this video where I'm showing you how to do anything. I'm simply pointing out that here's a 4th degree polynomial, and it has 4 roots. 3, 3, 2 plus radical 5, and 2 minus radical 5. I don't know if you notice this asterisk here, but when we say that an nth degree polynomial has n roots, or specifically in this case, a 4th degree polynomial has 4 roots, we really have to count what's called multiplicity. In this case, we say that 3 is a root of multiplicity 2 because it appears twice, one coming from each factor of x minus 3. We also would call that a double root. And in general, we would write our factorization in a slightly different way. The bottom line is that the fundamental theorem of algebra states and implies that whatever the degree of your polynomial is, that's the number of roots, counting multiplicity, that you should expect that polynomial to have. Let's look at one more theorem of importance called the rational roots theorem. I'll pause while you read this. Again, this theorem may seem kind of abstract, so let's look at a particular example of this. Take this polynomial, for example. The question may arise, does this polynomial have a rational root? It's a 3rd degree polynomial, but we know it has 3 roots. The question isn't, does it have roots? The question is, out of the 3 roots we know it has, is one or more of them rational? Well, the answer to that question is going to depend, according to the rational roots theorem, on the lead coefficient of 4 and the constant coefficient of 15. And if there is a rational root to this polynomial, it's going to be of the form number over number, or integer over integer, as all rational numbers are, where the numerator is going to be a factor of the constant coefficient, and the denominator is going to be a factor of the lead coefficient. For example, perhaps 5 halves is a root of this polynomial. After all, 5 is a factor of 15, and 2 is a factor of 4. Well, that doesn't guarantee that 5 halves will be a rational root, but it is a possible rational root based on this theorem. Is 5/2 actually a rational root to this polynomial? Well, to find out, we'd have to actually plug in 5/2. I did that. 5/2 is not a rational root. Is 15/1 a rational root? Well, according to the rational roots theorem, it might be. After all, 15 is a factor of 15, and 1 is a factor of 4. By the way, 15/1 is an integer, of course. The rational roots theorem doesn't say that 15/1 is a root. It says that it might be. That's essentially the implication of it. Is 15 actually a root to this polynomial? Well, I plugged 15 into the polynomial. I didn't get 0, so I guess 15 isn't a root either. Maybe -3/4 is a root. After all, -3 is a factor of 15, and 4 is a factor of 4. The rational roots theorem doesn't say that this must be a factor, a root of the polynomial. It essentially implies that it might be. It does meet the criteria. Well, to find out if -3/4 is a root to this polynomial, we'd have to plug it in for x and work it out and see if we got 0. I did plug it in for x and I did work it out and I did not get 0. So -3/4 is not a rational root either. Well, I've just showed you a few examples, but it turns out there are 24 possibilities. If I were to pick any factor of 15 divided by any factor of 4, you don't have to know why I got 24 possibilities. I wrote them all out. There were 24 of them. It turns out we still want to answer the question, does this polynomial have a rational root? Well, the only way I would know that is to plug in all 24 of those possibilities into the polynomial, one at a time, hoping to get a result of 0 and thus proving that it does have a rational root. Well, I did that with all 24 numbers. And every single time I plugged in a possible rational root to this, I didn't get 0. And that proves to me, and you don't see the work here, but that proves to me that this polynomial doesn't have a rational root. You see, the rational roots theorem doesn't state that polynomials have rational roots under a certain condition or another. The rational roots theorem simply states that if there is a rational root, it will match a certain format. In this case, it would have to be a factor of 15 over a factor of 4. But I tried every factor of 15 divided by every factor of 4, and I failed 24 times to find a rational root. Well, therefore, the rational roots theorem says that it doesn't have one. So just out of curiosity, I put this polynomial into some computer software and I found the non-rational roots. There are 3 of them, and they're quite ugly. In fact, the top one is real, but not rational. And the bottom 2, you can see the imaginary term I in there, showing that 2 of them are non-real. So this doesn't have a rational root. But it was worth examining the concept of what the rational roots theorem says. Now let's move on to the next component of this video, where we look at more practical applications. We're going to now see the kind of problems that you would see in a mathematics course, and you'll see some of the actual steps that you would take. What motivates these steps and what allows us to take them is justified by the theoretical part of the video that you just saw. Let's now look at our first example. Here's a polynomial. We may be asked to either factor this polynomial or to find the roots of the polynomial, or perhaps both. Let's examine both possibilities here. But in order to do either, one thing that we're going to have to do is find a root. because as we know, roots and factors are related. For example, if I were able to prove that 4 is a root to this polynomial, then x minus 4 would be a factor. If I could prove that 7 is a root to this polynomial, then x minus 7 would be a factor. If I could prove that negative 3 was a root to this polynomial, then x plus 3 would be a factor. And because of this interaction or connection between roots and factors, if I can find one number that is a root of this polynomial, I may be able to proceed and make some progress towards finding the rest. But the problem is that the only tool that we have to find roots or factors of a polynomial is the rational roots theorem. In other words, we have to find, or hope at least, that one of the roots to this polynomial is rational. And as we'll see in a few moments, that will lead us to the other roots. But in order for us to find a rational root, it would have to be some factor of 34 divided by some factor of 10. So it turns out there are 32 possibilities of factors of 34 divided by factors of 10. I'm not going to write any of them out here, but you can imagine that there'd be a lot of such possibilities. Instead of writing them all out, which I did do on my scratch paper, I want to take a special look, in particular at this combination here. Because 2 is a factor of 34, and 5 is a factor of 10, and so it is certainly possible by the rational roots theorem that this could be a rational root. The only way to know for sure, I suppose, would be to plug in negative 2/5 into the polynomial. Now I did in fact work this out, and I got 0. So great. By some sort of dumb blind luck, I've managed to find a rational root to this polynomial. And that rational root happens to be negative 2/5. But I want you to follow me on this mental journey. If there are 32 different possibilities, and for each one I had to plug it in, as you can see here that I did for negative 2/5, and work all of that out and find out if the result is 0, you can imagine that that would be kind of cumbersome. Luckily, there's a fast way to plug a number into a polynomial, and it's called synthetic substitution. You would have learned of it in the same video that you watched the synthetic division. And this process here, which I will not specifically go into in this video, but you should definitely watch a video on synthetic substitution or synthetic division if this looks unfamiliar to you. But what this shows is that after using synthetic substitution, the 0 here at the end does in fact prove that if I were to plug negative 2/5 into this polynomial, I get 0. Now it's still a decent amount of work, and one might wonder, well, why should I learn synthetic substitution to plug negative 2/5 into a polynomial when I could simply just plug it in the old-fashioned way and grind it out? Well, it turns out there's an added benefit to synthetic substitution. And the benefit is this. Once you get a 0 as your final remainder, or polynomial value for the particular input of negative 2/5, the synthetic substitution method is better because we now know that x plus 2/5 is a factor, and we further know that the bottom row of this synthetic substitution / synthetic division process will lead us to the other factor. And now I know that this is a factorization of my original polynomial. Now, there's nothing wrong with leaving it in this format. There is a slightly nicer format that you can do. Watch this cool trick. Looking at the polynomial on the right, notice that I can factor a 5 out of that polynomial. I'm not suggesting you would have to, but watch this cool trick. I've factored a 5 out of the second factor of this polynomial. Fair enough. Doesn't seem to have simplified it much. But what if I were then to take that 5 that I factored out of that polynomial and distribute it into the other polynomial? If I did that, I wouldn't have fractions anymore. Now, none of this is required, but don't you prefer, or wouldn't anyone who likes neatness in math prefer the bottom factorization of this polynomial to the top one? They're both correct, of course, but it looks nicer without fractions. Now, in terms of finding roots, what if we were to take this and apply the quadratic formula to it to find its roots? Well, I did that on scratch paper, and I got these two results. 3 plus radical 2 over 2, and 3 minus radical 2 over 2. And so after going through this process, I can now answer the question, what is the factorization of the polynomial, and what are the roots of the polynomial? The factorization is right here, and the roots, including the negative 2/5 I found originally by blind luck, along with the 2 I got from the quadratic formula, provide me with a total of 3 roots to this third-degree polynomial. Let's take a look at our second and final example. Suppose we're given this polynomial and asked either to factor it or to find the roots. It's really the same question, more or less, in terms of procedure. So here we have a fourth-degree polynomial. We should be expecting 4 roots. And again, the only good way to find one is to accidentally guess a rational root. And so, in order for there to be a rational root, according to the rational roots theorem, it must be a factor of 80 over a factor of the lead coefficient, which is 1. Well, restated, that just means that for something to be a rational root here, it has to be a factor of 80. But there are 20 possible factors of 80 if you count all the negatives. So what we're going to have to hope for here is a little bit of luck. Through lots of actual trial and error, I eventually accidentally discovered that 4 is a root to this polynomial. Now, one way you could do that is to plug in 4, although I didn't. I used synthetic substitution and ended up with a 0 here. And that 0 proves, in fact, that 4 is a root to this polynomial. Now, it's better to do the synthetic substitution for this, because not only do I know that 4 is a root, and of course, therefore, that x minus 4 is a factor, but I also know the other factor. And the other factor is going to come from these coefficients here on the bottom row. And if you make a polynomial out of those, we now not only know that x minus 4 is a factor by the dumb luck of finding that 4 was a root, but we now know the remaining factor. And therefore, my factorization of this polynomial, at least up till now, is this. But it turns out this second factor here may itself have roots and be factorable. Well, we know it has 3 roots. But the question is, are any of them rational so that I could factor this polynomial further? Well, the only way to know that is by guess and check. In order for something to be a root of this second factor, it would have to be a factor of 20 divided by a factor of 1. In other words, a factor of 20. Well, there are a lot of combinations of factors of 20, both positive and negative. So it is going to require a little bit of luck here. By some dumb luck, I discovered that x equals 4 is also a root to that second polynomial. And I found that out by doing the synthetic division process on that and ending with a 0. Ending with a 0 is great because it tells me that x minus 4 is a factor to that as well. But further, the remaining factor comes from the 1, 0, and the 5, which represents this polynomial, or as it's more commonly known, x squared plus 5. And so now I'm realizing that there is another factor of x minus 4, or a total of 2, in my original polynomial, I now have a further factorization for the original problem. And remember, each factor that you gather comes from the simple accident that you found a rational root, by luck more or less. Trial and error, really. And so now that I've found 4 was a root, and that 4 was a root of the remaining factor, I now have a further factorization here. In order to continue to find roots, by the way, we could write the factorization this way, couldn't we? In order to find any further roots, I would have to set the remaining factor equal to 0 and try to solve that. Well, that's something you can do using the quadratic formula or other methods you may have at your disposal about complex numbers. And ultimately, when we're asked to factor the polynomial or find its roots, we've got our factorization here, and the roots of the polynomial are all the things we gathered along the way. And that completes this lesson on polynomial factors and roots.